So good morning, good afternoon, and good evening. So now I will try to say some words on how to handle the recovery uncertainty, how to handle the so-called systematic effects that affect our measurement. In my presentation, I will start with some introductory information, like in the first one, and then I will discuss the type or list the type of reference materials that can be used to assess the agreement of the measured values and the conventional true values of the measurements. And then I will discuss how to calculate the mean recovery uncertainty. So I'll give some more examples than the one that I presented in my first presentation, and then I will discuss how to assess the mean recovery value and how to manage the variation of recovery with the sample matrix, rather difficult to handle, and what should we do or what should we expect when the results are not corrected for recovery. And then I will close with some final remarks. Okay, first of all, to remind us, why do we assess recovery? So the aim of recovery evaluation is to somehow quantify the between-day systematic effects on the results. So the preceding standard deviation already includes the between days and within day precision, and we need an additional component for the systematic effects, because our measurement uncertainty aims at producing, together with the measured value, an interval that includes the true value of the measurement with a non-probability. So the systematic effects must be considered in our evaluation. And it is important to mention that systematic effects can be constant in a relative way. So in many cases, we have relative systematic effects from analyte losses or from matrix effects. Typically, when we lose analyte, we lose more in absolute way if we have more analyte than if we have less analyte. So we have a proportional effect, and also matrix effects are proportional to the analyte level. In some cases, we have absolute systematic effects from contaminations, from additive interferences, but typically these additive systematic effects or the absolute systematic effects are more relevant in low concentration intervals or ranges. And the distinction between relative and absolute systematic effects or constant absolute or constant relative systematic effect is not so relevant in narrow concentration ranges. So to assess this recovery or to assess the systematic effects, typically you need to have samples with non-reference value. And we have different types of such samples, such items, such as certified reference materials. So we can use certified reference materials. For that, we can use results, samples from proficiency tests that I would say are similar to certified reference materials, except that they are not so stable through time. And we can also have a reference material that was characterized in another lab or using another method, and it will be a reference for the method that is being under development. And you also have spiked samples. And regarding spiked samples, we have two different types of spiked samples. Spiked samples without native analyte and spiked samples with native analyte that are already contaminated with analyte. And these spiked samples with native analyte are reference materials different from all the other ones. All the other ones, we can manage them in an equivalent way regarding uncertainty evaluation, but spiked samples with native analytes are different from the previous ones, because we have to estimate native analyte concentration, of course. The systematic effects are affected by the assessment of systematic effects are affected by measurement precision. So the systematic effects are systematic there for you, but to quantify them, to assess them, you need to perform some measurements, and these measurements are affected by precision. So your understanding of systematic effects is affected by the measurement precision. It is also affected by the reference value. So systematic effects are only assessed if you have a reference value, but the reference value uncertainty also affects your understanding of these systematic effects. And then the sample matrix in some fields affects the systematic effects, or the sample matrix affects the magnitude of the systematic effects. We can reduce the impact of measurement precision on our assessment of systematic effects if we analyze the reference materials several times, and if you take a mean of measured values. The mean of measured values is less affected by precision than a single value. So the first part we can minimize somehow. The assessment of systematic effects, in particular the proportional with an analyte, so that constant systematic effects in a relative way, is particularly or adequately assessed by calculating a mean recovery. Because in that case, the mean recovery should be rather constant in different concentration in a wide concentration interval. And this mean recovery is the mean of the measured value divided by the reference value. And in this case, we're using the mean because the mean is less affected by that precision component. So this is a rather useful way of handling these systematic effects. But I have to say that some authors only like to use recovery word when there is a potential loss of analyte from a sample digestion, from a sample extraction, and they prefer to use the word apparent recovery when we have a direct measurement of our sample without any sample preparation, and in fact what we see is the difference is difference between what we estimate in the reference value, having to account the direct measurement. So we know some preparation, we know expected and possible losses of the analyte. We will use this term in this presentation, recovery, for all these types of scenarios, both recovery and apparent recovery. Okay, like I mentioned in my first presentation, we need to do more than calculate the mean recovery and to calculate the uncertainty associated with mean recovery. We have to decide if the mean recovery is acceptable. Typically, we compare with the ideal recovery of 100% cases, and this is done using the test that I just described some minutes ago, where if this condition is valid, you don't need to correct the result for recovery. If this condition fails, and if you are allowed to, you should correct the results for recovery by dividing by the mean recovery. And how can we calculate the mean recovery uncertainty? To calculate mean recovery uncertainty, we have to take into account that this depends on the type of reference materials used. Typically, you have two types of reference materials. You have spiked samples with native analyte. That is a rather different scenario. And you have others. The others can be certified reference materials, samples from proficiency tests, spiked samples without native analyte. These are treated in a similar way, but in a rather different way from spiked samples with native analyte. The way that mean recovery uncertainty is calculated also depends on the number of reference materials that are being used to assess recovery. Typically, you have a general formula if you have several reference materials, but this general formula has a specific application when you only use one reference material. And the relevance of the sample matrix on recovery, the impact on recovery must also be taken into account in this calculation. Okay, let's start with a first example where we have a reference material that is anything except spiked sample with native analyte. Can be a certified reference material, a spiked sample, sample from a proficiency test, and you only have one. Not the ideal scenario, but okay, it can happen. In that case, typically you should analyze that reference material in different days, because you want to have this between the systematic effects. You do that over different days, different days, and then the mean recovery will be, of course, the mean recovery will be the ratio between the mean measured value and the reference value there, and the standard uncertainty associated with this mean recovery will be the mean recovery times the square root of two terms. This term is the relative percent standard deviation associated with measured value, with mean value, because we have this square root of m. So this is the intermediate percent standard deviation associated with the measured values, the mean of the measured values, square root of m, number of measured values. So let me repeat, this is the relative standard deviation of the mean under precision conditions. And typically you perform more than 10, m larger than 10, and you can estimate the standard deviation directly from your measurement results. And this is the relative standard uncertainty, associated with the reference values, as you can see from the slide. But sometimes, frequently, you have several reference materials available, and you want to take all these reference materials into account to calculate the overall recovery, and then you have to calculate the uncertainty of this overall recovery. And typically, each of these reference material, each of these reference material is itself analyzed n I times. Okay, so imagine you have three certified reference materials, and one is analyzed 10 times in different days, and another is analyzed 50 times, and another is analyzed 20 times in 20 different days. So this model takes into account that the mean recoveries for each material that are combined in this formula can result from different number of replicants. What we have here is an unweighted mean recovery, I would say, where you take all the recoveries and divide by all mean recoveries divided by a number of reference materials. Okay, but you can use a more complex formula where we have a weighted mean that takes into account more the mean recovery estimated for a larger number of degrees of freedoms. I can send you a reference if you want to use such algorithm, more complex. But usually you don't need to go more complex than this simple mean recovery. And the standard uncertainty of the mean recovery is, like I present to you in my first presentation, square root of the sum of different of these terms. So this is for each reference material. This is the respective mean recovery. Okay, this is slightly different from my first presentation, because at this stage we allow that each reference material can be analyzed several times. So here we have this additional term together with the % standard deviation and the mean measured value of different reference materials. We have square root of n number of replicates, and for each reference material we have the respective reference value uncertainty in a relative way. If the reference material is analyzed, if this n is smaller than 10, I would say this precision should be estimated from precision models, because you don't have enough replicates for that. So this is what you can see in the slides there. Okay, let me give you an example. Determination of period in waters. This is an example that was published in Talanta, and in here what we have, this was determination of period in waters after some preparation, HPLC determination, and here we have different waters, different natural waters and one treated wastewater. They were spiked at this mass concentration. This is the uncertainty of the spiking. The sample had no native analyte, okay, of course. And then this is the mean of the measured value. So, and in this case we measured 5 times, 10 times, 5 times, and 5 times. And here we have here the precision standard deviation. In these 3 cases, this was not estimated from the 5 replicate analysis in 5 days. This was estimated from precision models, and here it was estimated directly from the 10 results. Okay, so this is street precision. For each of these lines, we calculate this term that we call it T for term. So you have the square of the mean recovery. Then you have the terms that I just mentioned. These are the numbers there. And then we take the formula and get the standard uncertainty associated with overall mean recovery. Rather trivial to do. You just need to do it to understand the logic. Okay, and after doing this, after collecting the mean, calculating the mean recovery, the overall mean recovery, and to calculate the uncertainty of the mean recovery, we have to check if the mean recovery varies significantly with the matrix, the water matrix in this case, to understand if we need to add additional uncertainty component for the impact of matrix in recovery. How can we do that? We can do that easily by taking any pair of recovery value. Imagine sample A and sample B. If the absolute value of the difference of mean recoveries is larger than 2 times the standard uncertainty of the difference, it means that these recovery are significantly different. And you have 2 options. You can divide the scope in types of matrices that have equivalent mean recovery. Okay, you can do that. Or you can take everything together and add an additional uncertainty component for the impact of matrix on recovery. And typically you do that at the precision component or at the precision component by adding to the intermediate precision standard deviation or relative standard deviation, depending on the interval that you use for your for your assessment. You can use, you can add the relative standard deviation of mean recoveries. So this is for mean recoveries. You can add this relative standard deviation of mean recoveries times 2 times limit of quantification at interval 1 or directly for interval 2. Okay, this standard deviation is for the mean recoveries. So it will be typically if matrix is not important, this will be lower than this precision standard deviation. Okay. And let me give you an example. Determination of pyrene in waters of the other mentioned publication. So in that case, what we have in front of us. So we have here the 4 spiked samples, okay, 4 mean recoveries, 4 standard uncertainties of mean recovery. So calculated the mean recovery and uncertainty associated with mean recovery to each different reference material. So we use the formula, the previous formula, where only a reference material is considered, okay? And then we compared all pairs, first spiked sample versus second, third, and fourth, and so on. And in this page, in this slide, what you see is the ratio between the absolute value of the difference of mean recoveries, okay, divided by the standard uncertainty of the difference of the mean recoveries. If this ratio is larger than 2, the mean recoveries are not compatible. In this case, they were all very compatible, so there is no need to take into account the variability of recovery with sample matrix. But we had another example where this is relevant. We have other examples where this is relevant, and we have to take that term into account, the term that I just mentioned in previous slide. Okay, and now what about a reference material, that difficult one, that is a spiked sample with native analyte? This is a particular case of a reference material because we have to quantify native analyte to calculate the analyte recovery. And the example that I will present to you is a situation where we have the same sample with native analyte. We spike the sample, and then we analyze the sample without spiking and with spiking in the same day. Okay, in that case, what we have is a mean recovery, that is the mean of the measured value after and before minus the mean of measured value before the spiking divided by the added analyte, the spiked analyte. And the uncertainty, and sorry, it is necessary to mention that for this equation, the sample before spiking was analyzed m times, and after spiking n times, and everything done in the same day under repeatability condition. So the standard uncertainty associated with mean recovery, in this case, will express the recovery of analyte specific to that day. So this is a limitation, of course. This can be a problem if the recovery varies significantly between days. And the standard uncertainty of this mean recovery will be the mean recovery times the square root of 2 terms. So this term will be the square of the standard uncertainty of the spiking. So this is attribution from there. And the other one is the relative repeatability of the difference, or to be honest, the square of that, of the relative repeatability of the difference. And it is important to mention that this is repeated conditions because everything is done in the same day. And okay, of course, there is a chance that this mean recovery that was estimated in this day is not really adequate to describe what happens in different days. So, in fact, what labs do more frequently is something more complex. So they analyze different samples with different native analytes, and they spike different amounts to that samples. Okay, but when they do that, they must pay attention. They must be sure that what they add is significantly more than what was already there, native. We have that experience, but sometimes labs fail. But the questions that I present to you detect that problem. So, but before that, let's discuss how to calculate the mean recovery. So the mean recovery is the mean of all estimated recoveries, okay? And all estimated recoveries, each estimated recovery is the mean of estimated analyte level before and after spiking, divided by the spiked. Okay, and we divide by the number of materials, of samples that are being analyzed. Yeah, typically we do this in different days. So, since typically the pair before and after spiking are analyzed in the same day, the precision conditions in these recovery determinations are repeatability, okay? And typically what we have here is the standard uncertainty for the mean recovery will be the square root of the sum of all these terms. The n is outside again, following correctly the segregation law. This is for each spiked sample analysis. This is specific mean recovery, and then we have this term for each spiked sample. That is the precision of the difference of value before and after spiking, and this is the uncertainty from the spiking process. So we can do this together, and this should be okay, just like that, to be combined with the precision component if the recovery is not varying with the matrix. So if after doing that, you have to compare each mean recovery from each spiked sample and to assess if they are compatible. If they are not compatible, we have to take into account an additional component, as I described to you, for the precision, or for the variability of recovery with the different samples. Okay, we can also combine together results from different types of reference materials, proficiency tests, samples, certified reference materials, spiked samples with and without natives. You can take everything together and calculate overall mean recovery. This overall mean recovery can be a weighted mean recoveries if you take into account that some of these mean recoveries have more statistical quality because we're based on more results. Okay, we can do that, and then we combine them using pooling all the mean recoveries, and of course after that you have to assess if you need to correct for recovery, and if you need to take into account the between samples recovery. And this is a way of handling all the available information. And the equation that I just present to you for native analyte takes into account the cases where if your addition is too small, the uncertainty will. And now, I would say a more difficult situation to handle. What should you do when we are not allowed to correct the result for recovery? Or we are allowed to do it, but we decide not to do it because we don't want to have an additional correction factor. Okay, in that case, we should take into account that the option for not correcting for recovery will impact should impact on your result, should impact in your understanding of the measurement, and some analysts suggest to increase the uncertainty because we decide not to correct for recovery. So there is a rather old document that proposes something that I named as bias compensated expanded uncertainty, I would say, where you have the expanded uncertainty and then you have here the bias. In this reference, they use delta for this bias. You can calculate it as the measured value times the absolute value of the difference between mean recovery and 100% divided by the mean recovery. Okay, but this formula has several problems. One of the problems is that it's not following what is proposed in GAM regarding how to combine uncertainty components. We have a linear combination, and in fact, if you do like that, it is not similar to correct results for recovery. You somehow increase the uncertainty, fix the problem, but the interval, the coverage of the interval will not be the same as results correct for recovery. So in fact, we are your simplification, even by increasing the uncertainty, is not solving the problem. The North Test Guide suggests another way of dealing with these results not correct for recovery. In fact, the North Test authors say that you can even use this formula for results correct for recovery, but if you take your bias value, you can use this formula to increase your uncertainty for cases where you did not correct for recovery. And this formula is for the precision component. So what is suggested in this document is you take the precision component as described, but for recovery you use these formulas, and as you use these formulas, you don't need to assess if the mean recovery needs to be correct for recovery. But these formulas are pragmatic formulas, empirical formulas, not defined by applying the progression law to a specific situation. And I would say that as in this other case, the coverage interval will not be exactly the same as correcting the result for recovery. So any of those approaches, and there are even alternatives to these ones that are not equivalent to correct results for recovery, as described previously. So let me close with some final remarks. Some people, when they start to do uncertainty evaluations, find the formulas complex. And for them, complexity is always a major issue. But look, formulas are only complex before you apply them for the first time. And you can make the application of all these formulas rather easy if you use software, validated software. And the use of software makes calculations so easy that you can even use them in routine. So probably most customers from labs or when I use the word customers, can be anyone interested in your results, can be your colleague from a research project. So most customers will not value an accurate, more detailed evaluation of measurement uncertainty, but assessors will. And you as an analyst and your colleagues will understand and will value when the measurement uncertainty is more carefully assessed, more carefully managed, when uncertainty is compatible with the quality control, and you feel more comfortable when someone asks you to take decision on your results, when the evaluation of measurement uncertainty is under better control. Okay, thank you very much for your time and attention.